Good morning, guys. Good morning, everyone. Welcome to another episode of Xah Talk Show. We are going to code geometry, mathematics, graphics programming using wolfram language. So if you are here, say hi. This is like randomish. So I'm just gonna work on my website. You are looking at a visual dictionary of spatial plane curves. Search for it, you will find it. This is mathematics, geometry, pertinent to those of you studying calculus or college students. Elementary, this is like college level. If you are watching this offline, play at 1.5 speed. What I'm gonna do is I'm just gonna work on my website. And if you have questions, you can ask me about programming, about mathematics, and otherwise you can watch me code or for sleep, something like ASMR stuff. Okay, so we're gonna go slowly and drink. So if you don't know already, my gears like Emacs, the most advanced text editor, and okay, if you don't know my gears, well, let me show you. Okay, so Xah Talk Show, today's talk show 2026, March 4th, episode 774. So let's go down. So we are in Emacs, delete that, show in browser. So now it's better, and delete that to do back. So I'm using this Ultimate Hacking Keyboard 80, UHK80. You can find it in my reviews on YouTube, this keyboard, okay, UHK80, and that's NULEA, Nulia trackball. Fantastic. That's my favorite trackball. And this one is Logitech, very popular Logitech G502. I have it for like by now 7 years. I think I've been using it for 7 years. Okay, and I'm using Emacs, of course. And if you don't know already, actually show, let me show you a visual dictionary of spatial plane curves, okay? And search for it, you'll find it. And I'm using Xah keys, the most efficient key binding system in the universe, more efficient than Vim or NeoVim. There are videos you can watch, and it's download, it's free, it's for Emacs. If you are a programmer, if you are a writer, this would be most suitable. This is critical because it's gonna change your life if you are a writer or a programmer, because you're gonna, you need to write all codes, and this is the most efficient. Xah keys, Emacs. Okay, so what else? Let's see. And wolfram language, I introduced many times. Search for Xah wolfram language for programmers, xahli.info, my name. You'll find it. Complete tutorial from the ground up for programmers. If you know Python or JavaScript, it's fantastic, and you can download it free since a few years ago. The most advanced programming language by a magnitude. Wolfram language. Okay, so you can download. So, and that's what we're gonna do. So if you are looking at the thumbnail of today's YouTube, that's this one. Okay, let's run. Okay, so so shift enter. Okay, so it generates a new one. I don't want this one too big. Okay, let's just shift enter, and what? Shift enter generates a new one. Okay, that's a code. That is wolfram language you're looking at. Okay, so wolfram language download introduction, and you can download. I have like 100 videos about wolfram language. Okay, that's introduction about wolfram language. And what else? Let's go back. And today we're gonna use a lot of wolfram language packages for doing plane curves. So you can see it's all free. It's on GitHub. So just search for it. Search for wolfram language packages by my name. You can find all these packages. Fantastic and beautiful. Cheers. Red wine. You see, you're looking at this is nomos of the curve deltoid. Nomos of the deltoid. Let me just go over. This illustrates tangent. Nomos of a deltoid. Nomos of a parabola. Nomos of a asteroid. This star-shaped thing is called asteroid. We talked about in the past week. And the nomos of an asteroid forms another asteroid. You can see it forms another asteroid in different orientation. Fascinating. This is nomos of a cardioid. Cardioid means heart-shaped curve, this curve. And the nomos of a cardioid is another cardioid. You can see it generates inside the little, this is like an ass curve because the shape looks like an ass, but they call it heart because they, like the heart. But, they call it cardioid. But it generates a smaller cardioid inside. I should have the normal lines longer so you can actually see it. But is that actually true, or is it just looks like? You see, in mathematics, you cannot say something is true just by the look of it. You see, in mathematics, you have to do proof. Okay, so, but these visual tools illustrates the truth, or they can help you find what is true. Then you can do proofs, okay? Because when something is obviously not true, and when you do an illustration, usually it just doesn't work. You can tell that away it's not true. So anyway, so this is nomos of ellipse, okay? And they form a curve. I'm not sure there's a name for that curve, that thing in the middle. The envelope of the nomos of ellipse, okay? And this one is the nomos of deltoid. Jesus, why do I always have like nomos, okay? Anyway, so those all the above are nomos, okay? Then nomos are, by the way, nomos are the line that is perpendicular to tangent, okay? Now, if you don't know, let me just I can explain this. So even if you don't know any mathematics, you will understand. They don't teach like that in school. But so what is tangent? Tangent is the most fundamental intuitive idea. When you have a curve, like in a plane, like for example, this one, sine, that's a sine curve. And any point on the plane, then there is a line passing that point that is the most fitting at that point. You see, that line is called tangent line of the curve at that point. Okay, at the point on the curve, you see. So if the point is here, the tangent is this. If the point is there, the tangent is that. You see, there is one line such that it's like mathematically it's the most fitting. There's one. Now, how do you exactly define that? So anyway, I'm explaining to you the intuitive notion of tangent lines. It's like the most fundamental idea in differential geometry, which is the geometry for relativity. Okay, like most physics, differential geometry is basically when you study physics, it is differential geometry that is you would be concerned about, okay, about the universe. Okay, so tangent is the most fundamental idea. So you got tangent lines. So you see, so I explained the intuitive notion of tangent. You see, when you have a curve, like a smooth curve, and given a point on the curve, there's one line that's the most fitting. There's one and only one. Okay, so that's an intuitive notion. But what is it? How do you define precisely mathematically? Well, that's when you need to study analytic geometry. That's when you go to school to study mathematics. You see, you started to have a coordinate, x-axis, y-axis. Then you define, you can specify a point by the x, a number, x coordinate and y coordinate, and you can define a curve Now, by giving a function, like t x equals to this function's value, y equals to that function's value. So at any time t, you got two numbers, x and y, that specify a point. So at any time you got a point. So you started to have a curve, you see. And if the curve is smooth, that's advanced idea. So, but intuitively, we all think of curve as smooth. But anyway, so then you got a point on a curve. You can have a line is also a curve. So you can have an equation for a line. So you started to get precise, like mathematics, you can define what is a line, so then but basically the quick answer to the tangent is that tangent is a derivative for the functions of x and functions of y. Okay, now if you don't know calculus, you don't know what I mean, but that's, then you can learn it. But the intuitive notion that I'm explaining, the tangent line, okay, and in mathematics, basically that just means derivative of the x component function and y component. That's how you find the line. Well, you find the tangent vector, okay? That's like an arrow on this point, The length of the arrow indicates how fast the point is moving on the curve, okay? Anyway, so we talked about the intuitive notion of tangent, okay? Now, what is a normal? Like we showed many normals. Normals are very simple to understand. Once you got a tangent, the normal line of a point on a curve is the line that passes the point and perpendicular to the tangent. Okay, so all you have to do is find the tangent first, then you draw a line perpendicular to the tangent and passing that point, so for this one it would be like that. For this tangent line, it would be the normal would be that. The normal of the curve at that point would be something like that, and that here and that here. See, those are normal lines. Okay, these are tangent. Okay, so can we actually plot it? Yes, we can. You just type that. You can. should we plot it? So actually we can, but I have something else planned to do. Anyway, so actually let's plot it since we started to talk about this. Okay, plane curve plot. So let's go to okay, so envelope. Let's just go to let me just do my things. Let me just show you. Okay, we already have wolfram language open. So so you want to plot it? Easy. So let's see. So already paste and magnify, please, because otherwise it's too small for people to see. And what we want to plot is this sine curve, t and sine. So the parameters are, here is just t and sine, okay? So actually we can plot it and see what happened. Oh, it went crazy. So, so t to sine and t from 0 to 6, okay? So go back here, t from 0 to 6. So simple. I don't want that, super complicated. Delete t to 6, okay, 6, and caustic style plot range deleted. Okay, axis force deleted. By default, axis is true because we want to see the axis. Background hue 0, 0, 0. Hue 0, 0, 0 means black. I don't want black. Make it white by default. Aspect ratio automatic. That's good. Caustic line style. We don't want. By the way, what does caustic mean? Caustic is a ray from a light source. You see, you got this thing. This thing is a circle. You see, sine, cosine, sine parametric equation. That's the equation of a circle. So here you got a circle, basically half of a circle, because it goes from pi to 2 pi. You see, it adds a little number You see, we add those tiny number to prevent like division by 0 and division by infinity, something like that. So that's why we add those, but actually I don't think, may not be necessary. Let's try it again. You see, it's not necessary. So this tiny number, let's remove it. So in this case, we are plotting cosine and sine. Cosine t is the number for the x coordinate, a number, okay? Sine t is a number for the y coordinate, cosine and sine, okay? And t is time. You can think of it as time. So t goes from pi to 2 pi, and in steps of pi over 40. So 40 steps, okay? So we go over half pi in 40 steps. Shift enter. Fantastic and beautiful. That's what you see. So t, that curve is this one. And what are the lines? The lines are light rays, okay? Think of them as light rays. So we got that, which is called caustics, okay? So we got this caustic origin from 0, x coordinate is 0, and y coordinate is 5,000. Basically, it's a vertical line. The light source is very high above, above these graphics. Can you guys see me? Okay, if you are enjoying this video, say hi, okay? Say in the comment. Any questions, comment, you can say it. Okay, so you got this light source, like somewhere above, then it shoots a light down to the circle, then it reflects off when it hits the circle. That's reflects and refract. You see, some of them reflect, the yellow lines reflect, the red lines refract. That's how you get this thing, okay? Is that beautiful? Does that make sense? So that's this one, okay? So that's this one, okay? So caustic line style, we say random, we actually say random two colors, okay? But here we wanted to demonstrate this tangent and normal. So we want to do sine and cosine. T206, okay? Caustic line length, we don't care. Caustic origin, we don't care. Line length, we don't care. Plot dot force, we don't care. Anyway, let's just draw it. Let's see what happens, okay? Oh, you got this thing, okay? So let's delete that. Caustic origin, plot dot force. What else we have here? Oh, you missed the comma, that's why. Show. Okay, nothing. Okay, so caustic origin, so power plot dot force, plot curve force. Oh, obviously you want to plot a curve. Delete that. So if we show here plot curve, let's say, oh, you forgot the comma. That's why. Amazing, I forgot a comma there. Fantastic, you see, fantastic and beautiful. Plot curve, let's say true, okay? Plot curve, true. That's right. That's what we want. Shift enter. Fantastic and beautiful. I don't like this color, so let's do it again. Shift enter. Better, but let's try again. Shift enter. Okay, I like this better. So caustics means the light rays reflected from a curve. So you can see this blue is a circle, half of a circle, and the parallel light rays hits it from above. Then some of it reflected off. Then you got this thing, like S-shaped thing. That's called the caustics of this curve at a parallel rays. Okay, that's called catacaustic, and this refraction is called catacaustic, and what's the other word? Anyway, that's called caustics. Okay, that's like optics, the study of optics. So anyway, so we are trying to illustrate about this normals and tangency. We are trying to explain what is a normal. So what do we have here? Shift enter. So why are we plotting all these? Oh, you need. Okay, so you need plot range. Copy that. Copy. Okay, so you want a plot range here. Paste. Okay, plot range, let's say 0, let's say -6 to 6. That's for x. And y, let's say -3 to 3. Okay, shift enter. Fantastic and beautiful. So we started to see that. Okay, now we just delete all this. Actually, we don't need this. We don't want caustic. Delete it. Caustic line length. Delete it. Okay. Plot dots. Force. Delete it. Okay. Delete. Plot range. Actually, plot range also. Okay. Leave it. Curve style. We don't care. Delete. Okay. Now delete. Shift enter. Okay. We started to have a nice sign. Okay. Now plot range from 0 to 6. X 0. Okay, shift enter. Fantastic. Now we're talking. Now we wanted to show tangent line length. Okay, so let's give an option. Tangent line length. Let's say 10, 20. Okay, 20 is good. Shift enter. Fantastic. Can you see the tangent line at that point? Okay, now you need some you want to specify specific points for the tangent. Okay, so you gotta enter a point like that. So let's see. You gonna enter a. Okay, so let's say 1.5. Well, 1.5. When the t parameter is 1.5, what you get? Shift enter. Oh, there, right there. So that's your tangent line. Okay, now you also draw normal. Okay, so normal line length, that's what you want, 20. Okay, so you're gonna draw a line normal at that curve point. So let's do it. Fantastic and beautiful. Can you see? So now we have actually illustrated the concepts of tangent and normal. So let's change that again so that makes it more kind of makes sense. Okay, tangent and normal. Fantastic. So save this as untitled. Okay, let's save it. Okay, so we were explaining the tangent lines and normal lines of intuitively, and so we talked about this. So the review. Okay, so now you understand tangent and normal. So you see, these are normal lines to this triangular shaped thing called deltoid. Okay, now this is the blue is a parabola, and you draw all the normal lines to all the points on the parabola. You get this. They form this V-shaped thing, and I believe that's called semi-cubic parabola. Okay, you see, so we say that the envelope of the envelope of normals of parabola is the semi-cubic parabola. What was it called? Semi-cubic? I forgot. Anyway, so they form this shape. Okay, now this asteroid in the middle, this star-shaped thing, ninja dot. I call it ninja dot. So if you draw normals to all points on this asteroid, you get this another asteroid. Fascinating. You see, Then you draw the normals of that asteroid is another asteroid, you know, then it's just bigger. So it's like amazing properties. Okay. Then these normals of the cardioid, you get the smaller normal. So okay. So actually, did we, you know, we can actually verify. So, you know, so that the things we are talking about, this is this visual dictionary of spatial plane curves. They explain many of the plane curves definition and properties visually. So you don't even have to know any mathematics. You can see and tell. See and tell. You see, this is the definition of parabola. Can you like, you know, you should you should look at this and immediately like understand what is the meaning of parabola by looking at this closely. The meaning of parabola. Okay. Yeah. Anyway, so let's make that video loop because okay, showing browser. Go down. Let's play. It will loop. It will be better. Okay, so yeah. Cheers. So we talked for 30 minutes. We got a lot to go because I was planning to code, but I'm gonna code. Okay, so but first of all, what I've done is I taught you guys some elementary geometry of plane curves, especially the very interesting, fascinating aspects without having to know any mathematics. So for you programmers, you know, this would be hopefully it's interesting. Okay. We talked about tangents and normal lines, and so anyway, visual plane curves. Okay. So I wanted to see, yeah, we were wondering about you see, we were talking about cardioid, the normals of a cardioid. Do they form is this actually cardioid? We can look at here. So cardioid, because everything I wrote there, you know, I verified it long ago. So this curve is cardioid. You see, in this picture, it's formed by all its tangents. Okay, so anyway, the cardioid is normally defined as a curve rolling on another curve, like that. Okay, now, yes. Okay, so you can see properties evolute. The evolute of a cardioid equals to itself. Fascinating. So it is indeed true. That is what we were illustrating in this image. In this, you see, this is to illustrate that the evolute is another concept. But anyway, evolute is kind of like equivalent to the envelope formed by all the normal lines. So basically, this thing inside is another cardioid. You see, this thing, you see, is called cardioid, meaning heart shaped. But the things inside, that's another cardioid. Okay, fascinating. So anyway, we were talking about and here, so then we were talking about okay, normals of a deltoid. Then we started, so these are secant. Okay, these red lines are called secant. Okay, secant is basically just given a curve and given any 2 points on the curve, you draw a line between them. That's a secant. Okay, so secant doesn't have any like special meaning to a curve. Meanwhile, the tangent has very significant meaning on a curve. Tangent must be precise. Okay, and because tangent is basically the heart of calculus. Okay, like when you study calculus from a geometric point of view, the entire calculus is just about tangent. Okay, like how do you find, so there's this line that approximate a curve at that point, that's a tangent. Okay, so the entire calculus from a geometric point of view is just about tangent. Okay, that's one way to look at it. One way. Does that I'm thinking, how accurate is it? I mean, so that's interesting. You see, I made a random observation commentary extempore that I claimed that from a geometric point of view, tangent is what calculus is all about. So, but are they a part of calculus or analysis that's like beyond, is not based on tangent? Actually, I don't think so. So, that's a quite significant commentary. So, actually, so let's check AI to verify. Okay, so right now we digress into AI. Let's see AI. How good is AI? Can AI verify my claim, my extempore random observation? So the claim is, from a geometric point of view, tangent is what calculus. Tangent is the heart of calculus. Okay, is this statement valid? Let's ask Quark. Okay, so let's move that here. So that's like what we were talking about today. Showing browser. So this page is today's talk show notes. Okay, those are links we were talking about. So this is like what we were doing right now. So let's ask Guac. AI, help me. I don't know anything. I'm a zoomer. From a geometric point of view, tangent is the heart of calculus. Is this statement valid? Okay, let's magnify, control magnify. Let's see. Okay. Yes, the statement is quite valid, especially when viewed from a geometric, historical, motivational perspective. Okay, the concept of the tangent line really is one of the deepest conceptual heart, if not the heart of calculus. You see, particularly in the way calculus was originally discovered, invented. Amazing. Such a deep statement, such a deep observation. Here are the main reasons why this view is widely shared among mathematicians and good teachers. It says I'm a good teacher. Great. Historical origin. The tangent problem was one of the two birthplaces of calculus. Oh, tangent problem. Given an arbitrary curve, how do you define and find the tangent line at any point? Okay. Anyway, it's so, you guys can read about this later because we're gonna do some, we got more things to do, or you can ask AI yourself, but that proves my point. Okay. So anyway, so what is the reason that, let's just go over historical origin. The tangent problem was one of the first, was one of the two birthplaces of calculus. Okay, it says the derivative is literally defined via tangent. That's right. Geometry, you have the tangent, but if you do like algebra, that's basically, that means derivative. Okay, I talked about before, like 20 minutes ago. So local linear approximation, the most important idea in all of differential calculus. That's right, that's a tangent. Contrast with integral calculus. Well, okay, integral calculus, you got the kind of the area notion, infinite sum, but they are related, they are tied together by the fundamental theorem of calculus. Okay, so let's see what it says. Contrast with integral calculus. I dare you to ask Guok. I am I am a zoomer. Am I a zoomer? hello ACP. So then okay, contrast with integral calculus. While the fundamental theorem of calculus links differentiation and integration, the geometric heart of integration is usually considered to be the area under the curve. Okay, so this so you could say, so they are talking about the you see, normally calculus you can separate it into like differential derivative or differentiation aspect versus the integration or infinite sum aspect. You see, so one of them, one part of calculus, you call it derivative, you call it you call differential calculus. The other part you call it integral calculus. Like usually you can classify calculus, you can separate calculus into like these two branches, but that's shallow view. But usually in advanced calculus you don't do that. They are together because they are tied together by the fundamental theorem of the calculus. That's one of the most fascinating subject. You see, like when you study mathematics, like sometimes you can, when you learn some theorem, it sends chills down your spine. For certain people, for me, for example, that's when you are extremely obsessed about the topic, because then you learn something that's just amazing, that's just incredible. So one of the first, so in my life, I have experienced a few of them. Okay, one of them is fundamental theorem of calculus. Okay, that's amazing. So that's a amazing trip in mathematics. So I'm telling you guys, so you might get inspiration. You might, you can see how I find this mathematics so amazing, so fascinating. So you can see fascinating, this fundamental theorem of calculus. But I'm not gonna tell you what that is, because then it's like, then you need to study calculus. Okay, so I give you some motivation. So but because we are doing something else, we gotta do code and stuff. So you can, there's a lot other channels, videos you can watch, and professors you can go learn about calculus in detail. Okay, but we are doing something, a different topic. Okay, copy the link and go back to the talk show and post. So let's remove that. Remove that. Okay, that's my question. And Guok answers, yes, I'm correct. What Guok says. Fantastic. Okay. Okay, so we talked about we kind of random went over about, or like basics of plane curves. Okay, tangent, normals. Okay, let's go quickly. So we I'm just actually just beginning, like I'm trying to give you an introduction of some of the plane curve things, like why are we doing this, but we haven't begin to talk about what I wanted to do today. Yeah, so you see, you got quite a lot to go. Even we only talked about tangents. Okay, then we talked about normals, then we talked about secant. Secant is just like any 2 points on the curve given, then you can connect a line between them. That line is called secant for between that 2 points on the curve. Okay, so secant is not very significant. Okay, the significance is the tangent that like what we just talked about. That's like the heart of calculus. Okay, that's very significant. What about normal? Well, normal is just perpendicular to the tangent. Okay, so normal is basically like tangent. Okay, so like it's like another view. So basically normal is just tangent. I mean, like tangent. Okay, so secant doesn't mean much. Secant just you can generate pretty pictures. Okay, for example, this curve, this curve, by the way, is one of the fascinating curve. It's called logarithmic spiral, but a better name would be equal angular spiral. It's also known as equal angular spiral because when you draw an angle from the center of the spiral, it hits the curve. For any point on the curve, the angle is the same. Okay, it doesn't matter where. If you draw a line, a ray point, when it intersects the curve, it doesn't matter which line, the angle is the same. It's called equal angular spiral. Okay, of course, it's also on my website, visual dictionary of spatial plane curves. Okay, you go there. You go to spirals. Okay, so there, this one, equal angular spiral, and the mathematician Jacob says, when I die, I want this curve inscribed on my tomb. Okay, this guy, James Jacques Bernoulli, one of the mathematician family. So in 1600s, they lived. So you can go to Wikipedia. You can actually see the tomb, but I don't think that's a original. But people rebuilt it because it became very famous. It's such a. I talked about this before, like a few years ago, 2 years ago or so. But let's show it again. So you see, this is Latin. Means, although changed, I arise the same. Okay, so that's a tomb, or how do you pronounce it? Tomb on this mathematician's grave. But I think that's they remade. They remade these just to sustain this quote because that's what he wanted. But also very interesting is that you see they actually made a mistake. the guy drew a spiral that is not equal angular spiral. Okay, so you see, equal angular spiral has this property. Any line you draw from passing the center of the spiral intersect with the spiral in the same angle, in the value of the angle made by the intersection is the same, regardless what is your orientation of the line. Okay, that defines this spiral. Okay, that's when this spiral is called equal angular spiral, also known as logarithmic spiral, because the formula is a logarithm. Okay, somewhere. Okay, you can exponential. It's a logarithmic spiral. Okay, somehow I don't have the formula here. Annoying. I should add it. Because it's well known as a logarithmic spiral. In fact, logarithmic spiral is the name I believe more popular than equal angular. Equal angular spiral is a better name because it describes the definition, the definitive name for this spiral. It tantamount, it's equivalent to the definition of the spiral. Okay, when you say logarithmic spiral, well, that's because the formula turns out is a logarithm. Because if you but that's not a good name. Okay. Anyway, so that's a definition of this spiral, equal angular. Okay, so you can see the property illustrated here. You see, any line passing the center intersect the curve at the same angle. Okay, so this spiral is actually a family of spiral. It's not like it's not a single specific one. There's like a bunch of them defined by the angle. So given an angle less than 90 degrees, you got one equal angular spiral. Okay, that's a definition. Now, there are other spirals that's not like that. So, for example, this Archimedean spiral is not like that. Okay, you draw a line passing the center, it intersect the curve. Depends on the intersection have different angles depending on how your orientation of the line. Okay, so for this curve, that's it's not equal angular. Okay, it has other properties. Okay, other properties. That's why this is called Archimedean spiral. But the graveyard, the carpenter or whatever, he doesn't know about the mathematics, so he drew an Archimedean spiral on the grave. So that's funny. So you can read. So we talked, I talked about this like 2 years ago. I told this story. So you can go to Wikipedia. This is Latin, Edam mutata resurgo, something like that. So you can see. Interesting, because it's interesting mathematical fact. Okay, so so anyway, so that's a guy, Jacob Bernoulli, one of the great mathematician. Okay, so Wikipedia, of course, Wikipedia has an article on that. Wikipedia got all sort of articles. Okay, there it is. Logarithm. You see, they call it logarithmic spiral, but it's better. It's better. The better name would be equal angular spiral, because that name defines the spiral. That's a property of it. Okay, so there it is. So you can see the logarithm formula in Wikipedia. Do they show it? Like the formula would be there. Okay, you see that or that. You see, that's an exponential formula involving exponent, and here you rewrite it, so you got the logarithm, natural logarithm. Okay, so that's why I didn't include the formula. I mean, I have the formula here, so let's see, where is it? Archimedean, not Archimedean. So we want equal angular. So equal angular. So you go formula section, formula. So you got the exponent. E is the special constant. That how do they call that constant? Was that called Euler's constant? It's like, anyway. So maybe you guys get the idea. Okay. So anyway, I think I kind of just rambled for an hour. Is it 50 minutes? Not an hour yet, but we didn't get to do what I wanted to do. Euler. Okay, is that called Euler's number? Euler constant. Euler's constant. Okay, defined because it could be Euler constant means something else. You see, it's a bit tricky. You see, Euler constant means something else. Let's go there. You see, Euler's constant means this Euler-Mascheroni constant, which is 0.5 something, that which is not the other. The one we are thinking of is the other. I think Wikipedia will mention it to avoid confusion. The one we are looking at is called let's see. If you click on that, not logarithm there, the base E, you'll get to it. Okay, yeah, so there it is. Euler number. Okay, so the number E is a mathematical constant approximately equal to 2.718 something. That is the base of the natural logarithm and exponential function. It is sometimes called Euler's number. You see, by the way, that's called Euler. I think that's pronounced Euler, the guy's name. Swiss mathematician, Leonhard Euler. But usually I like to pronounce it Euler because that's how English pronounce it, Euler. Anyway, I think it's Euler something. But anyway, you can see that you see this number, mathematical constant E, is my wife is back. I should go to dinner soon. But you can see that this you see they don't have actually they don't have a name. They should have, but we don't actually have a name for this number. We usually just say E, the base of natural logarithm. Sometimes we say Euler's number, but it's different from this Euler's constant. You see, this Euler's constant is equals to 0.5 something. You see, very confusing. Okay, I think my wife is back, so let me say hi to her. Sweet family. When you have a wife, everything is good, provided that you have a good wife. In America society, you get a girl, you got a wife, you fuck, and you get divorced. You got in America society, you got lots of problems due to the huge amount of corruption in the past like 20 or 30 years. Okay, hold on a second. Let me say hi to my wife, and we'll be back. Hold on a second. Be right back. Hello guys, I'm back. Welcome back to the live streaming stuff. So I'm having red wine. My red wine is we out of red wine. So this is the last struggle of the red wine. Okay. We need to go by. So we were talking about the Euler number versus Euler constant. Very confusing. Actually, I don't know what is the Euler constant. I know it because of the Unicode. Because there's a Unicode for that, for this Euler constant. It looks like anyway, so let's not go over there. So but you see it's different from this E. So Euler number, okay, so like there is no, well, I guess the best name is just Euler's number, but very confusing with the Euler's constant, okay. So you see Wikipedia title, they even, they don't name it Euler's number. They actually, the Wikipedia title is like, yeah, the mathematical constant, but they name, here they say Euler's number, but was it Euler or Euler, something like that. So anyway, this number is significant, okay, especially in calculus because it is significant. Okay, so we talked about, like, we were just going over curves. Yeah, so we were talking about this logarithmic spiral, equal angular spiral. And we mentioned this mathematician, who has this on the grave, and the engraver got it wrong. They got the Archimedes spiral. Quite funny. Okay. But anyway, so but why are we talking about the spiral? That's because, that's because of, from this illustration, we happened to use secant to draw pretty pictures of this equal angular spiral. Okay, so that's why we started to mention this Jacob, Bernoulli, and logarithmic spiral, stuff. Okay, so you see, so basically today we are actually just going over my plane curve package, wolfram language package. You can download it here, and showing you the example illustrations feature gallery. And I was just going through them and doing explanations on why they are interesting. Okay, like these are the fundamental interesting concepts in analytic geometry with respect to calculus. Okay. So we talked about tangents, normals, and secants, okay, and equal angular spiral. And this is this star-shaped thing that's a hypotrachoid, which means you roll a circle on another circle, inside another circle. We talked about, like, yesterday many times in the past week, several videos. And this, it just generates pretty pictures, okay? And hypotrachoid, okay, so also known as spiral graph. Okay, then there's optical properties, like we talked about caustics. Okay, of parabola, the most well known. For example, we can see it in flashlight. This parabolic mirror. Okay, then there are several. Okay, so optical properties of ellipses. Have you guys seen the elliptical pool table? That's if you guys know interested in mathematics, you have seen this, because this is the most like interesting thing. So it's a pool table, but it's an elliptical shape, But if you don't know mathematics, you probably never seen this before. But I'm showing you for the first time. So you see, you got a pool table. A lot of people are interested in this. But if the table is shaped like an ellipse, then you got properties such that they reflect from one point, it will bounce off the table to the other point. Those points are called focal of the ellipse. Okay, very interesting things. So there's a lot pictures, and people have built elliptical pool tables. Okay, so those are, it's for you nerds. Anyway, so it's like a common topic talked about for like 50 years or more. So anyway, where am I? Where was I? So I'm now right now 20% drunk. So that means we're gonna stop. Okay, so shit. So as far as this package goes, there's so we can talk about caustics. One feature of the package is to draw caustics, so you can see caustic length, to allow you to visualize optical properties. So for example, this one we used in our thumbnail, kind of similar to that. Then you can also draw osculating circles. Now, osculating circle is the most interesting. Osculate means kiss, okay, in Latin, I believe. Osculate means kiss in Latin. Osculate is a versatile verb with meaning spanning affection, biology, and mathematics. Okay, affectionate kiss. Osculate to mean kiss. Okay, so but what is origin? So the word originates from Latin osculum, meaning little mouth or kiss. Okay, so from Latin. But basically, osculating circle means that, where are we? Shit. Okay, that's osculating circle is like tangent, like the idea of tangent, but it's a circle that is the most fitting circle at that point on the curve. So given a curve and given any one point on the curve, you have a circle that kind of is the most fitting to that point. Okay, so for example, this point on this sine curve, at this point you got this circle. This circle is called the osculating circle at that point of this sine curve. Okay, now how is this curve defined? Basically, this circle, how is this circle defined? The circle is basically the most fitting circle that fits the point, which means basically the curvature, the concept of curvature. Okay, so the concept of curvature means, which is very intuitive. Like if, for example, here the curve is very more tight than over here. For example, imagine you are driving a car around this ellipse. So over here, when you pass, you don't feel much, sway. Like, but if you are driving at the same speed, when you pass over the major axis, then you feel like there's a like strong sway, right? So that's a concept of curvature, because at that point at the major axis, then over here. So you guys see what I mean? So that the concept of curvature is captured by this so-called osculating circle, okay, at any point on the curve. This is fantastic concept. Anyway, so then we can draw so osculating circle also, you can just call it kissing circle, okay, kissing circle of a point on the curve. So you can draw that for spirals and for cycloid. Now this curve is another fascinating property. This curve is created when you draw a circle on a line. So for example, the bicycle, if you ride the bicycle at night, you attach a LED or reflector on the wheel. So as you ride along and onlooker, you'll see the light will trace out a curve like that on the wheel, okay, on the rim of the wheel. This curve is called cycloid, okay, that's called cycloid. Why is this curve interesting? Because this curve happens to be the optimal curve if you want a ball to fall down, to roll down from one point to another point on the ground. Okay, like you can have a straight line, or you can have like a semicircle, or you can have however curve you want. If you want the fastest curve according by gravity, then the optimal path is this cycloid. Okay, and this cycloid is defined by rolling a circle on a line. Okay, so that's why, for example, you can see an animation. This is why this visual dictionary of spatial plane curves are so interesting. That one, cycloid. Okay, so you can see an animation there. Okay, so why is this interesting? Because that is the solution to the Bracken the problem called Brackenome something. Okay, that is the like what is the path so that when you place a marble, it will fall down the fastest. So if you search on the web, Wikipedia, and you'll see lots of answers. Okay, cycloid. So just search for the curve cycloid. Okay, okay, that is the cycloid curve, and the reason we are talking about that is because, again, this package can draw it. I mean, it can draw the evolute. Okay, evolute is again is the locus of kissing circles. Okay, so cycloid, which is a curve traced out by rolling a circle. Okay, it has a property such that the locus of its kissing circles, all the centers of the kissing circles on the curve is itself is another cycloid. Okay, you can see here. So the package just illustrate that. Okay, so you can type this and you'll draw that. Anyway, that's this is called evolute. Anyway, asteroid also has that property. The evolute of asteroid is itself. It creates another asteroid. Okay. Anyway, so we started to show, we just talked about the properties of these So this features of this package. Okay, so again, you can get it. Just go to GitHub by search for Wolfram language packages by Xah Ep774 and Wolfram plain code package. You can get this package. It's on GitHub. Okay, and we basically today we spend 70 minutes going over on why this is interesting. So let's turn on JavaScript. Okay, I think that's it for today. Actually, wait, don't I have any, wow, I didn't add any graphics. What? Did I not add any graphics? Amazing, I didn't. On the, what? I didn't? Interesting. So let's go to Git directory and plain curve. Let's go to plain curve plot. So here is the package, but wow, I didn't include any images. Amazing. But I did include it on my website. You see? Okay, so I got so there's things to do there. I need to update the GitHub. Anyway, I think I'm like 20% drunk, and there's a lot coding I need to do, but I don't feel like doing it right now. So there's more to it. Okay, so there's this caustics optical properties. There is the kissing circles, which creates evolutes illustration. Then there's more. There is there's also radio, which is very much related to kissing circles. Okay, I'm not gonna explain because I'm kind of tired and drunk. And there's conchoid of Nicomedes. Okay, that's another way to generate a curve. Okay, so again, it can be done by this package to illustrate it. Then there is conic inverse into Lemicon of Pascal at their focus. Okay, so there's inversion. So you can invert a curve with respect to a circle. For example, this picture shows the inversion of a parabola with respect to the circle centered at the vertex of the parabola. Then you get these red dots. Okay, that's an inversion of the parabola at the vertex of the parabola. What you get, the red dots, is the seesaw of Diakos, a very ancient curve, like 2,000 or 3,000 years old. So seesaw of Diakos, what is the property of the seesaw? It is this one, okay, this curve. I think it's a cubic curve. What's the property? I forgot. Okay, but you can look up. Let's see, plane curves. So seesawoid. So you need to go to check seesawoid. Let's see, Asian curve, seesaw of Diakos. It's a curve created in 2050 BC, so about 2,000 years ago, trying to solve the doubling the cube problem. Okay, so anyway, so it looks like that, kind of like a ivory. That's what seesawoid means. Okay, so the name seesawoid means ivory ivy-shaped, ivy, which is a plant, okay? But anyway, so this curve is, it's called seesaw Diakos. I'm not sure how to pronounce the name Diakos, but anyway. This curve is created 2,000 years ago, okay? And what we are talking about is that parabola, the inversion of parabola at the vertex of the parabola is a seesaw of Diakos. Very interesting, okay? And inversion, there's lots of other properties. Inversion of a hyperbola, lots of, okay? So we haven't, okay, I'm not gonna go over them. Anyway, so today we basically just went over this package, plane curve plot package, and why it the features, why it, many of the features does interesting illustrations like fundamental to plane curves geometry. Okay, that's it for today. Okay, bye guys, bye.